All right, so you guys, for this class on graphing functions and transformations, we're in luck because in grade 10, we've already learned the transformations and the words when we did parabolas. So what we're going to do is we're basically going to split up all the transformations. And in today's class, we're only going to talk about vertical translation, so moving up and down, and horizontal translation, moving side to side. The only difference is when we were learning about parabolas, we use a step pattern. Now we can't use a step pattern because our functions are a little bit more complicated, like the rational function. So we're going to use something called mapping coordinates, and that's what we're going to go over today. So let's look at vertical translations. You guys should remember from parabolas that whenever you have a number outside of your function, that refers to your vertical translation. It tells you how much your graph is moving up and how much your graph is moving down. So to illustrate this, we have a random graph on the right-hand side. And to this graph, we're going to do two different transformations. One of them is we're going to +2 means we're going to move the graph up 2 units. And the other one is -3. We're going to move the graph 3 units down. And you're probably saying, well, this is pretty easy. I'm just going to take every point and move it up 2 units or move it down 3 units. And you're right. However, that way is going to be very inefficient when we get into more complicated functions. So we need a method that works all the time. And that's why we're going to rely on a table of values and mapping coordinates. Okay, so let's begin by first just identifying a couple of key points on this graph, which are wherever the lines meet. And we're going to write them down on the left-hand side where it says x comma y. So we have -3, 0. We have -1, 3, 2, -3, and 4, -1. Question? You could absolutely, you could pick any point that is pretty obvious. Okay, so for the first function, like I said, y is equal to f of x, which refers to the graph. In fact, we can go ahead and label this graph y is equal to f of x. So we're taking this random f of x graph. We don't have a name for it because it's not a particular function. And we're adding 2 units vertically. If we're moving this graph up 2, is our x value affected at all? No, the x values are not affected, but every y value is going to move up 2 units. So our mapping coordinates for this would be our x values all stay the same, but our y values are now going to have +2 added to them. Sarah? Yes. In this case, f of x refers to this function. So it's saying this function we're going to call f of x. And now we're going to take the function f of x and we're going to move it up 2 units. Okay. Yep. The x. Yep. Yep. Good question. Okay, so none of our x values change. They're going to remain the same. So -3, -1, 2, and 4. I'm getting that from over here. I'm going to rewrite it. It's still going to be the same. But for our y values, we're adding 2 units to every single one of these y values to give us brand new y values. So what's that going to look like? Well, for the first example, we have a 0. When we add 2 to it, it's just going to become a 2. For the second one, our y value is a 3. 3 + 2 is 5. For the next one, -3 + 2 is -1. And for the last one, -1 + 2 is +1. So these are our brand new coordinates. And when we graph them, we should see our entire graph. It should retain the shape of the original function, but every single point should move up 2 units. Question? The y, yep, every y value. Yep. I'm going to label it y is equal to f of x plus 2. And visually, you should be able to see that your entire graph has moved up 2 units. Every point has shifted up 2 units. Let's answer a couple of questions. It says, what is the value of C? The value of C in this case is just the number 2. Describe the transformation. We're going to say it is a vertical translation 2 units up. And this should be very familiar to you from graphing parabolas because the words and all of that stuff stays the same. So horizontal, the number is actually going to be attached to the x, and we're going to do examples of that after we're done the vertical. So I'll point out the difference. Yes. Okay, let's go ahead and do the exact same thing now with the same function, but it's going to be f of x minus 3. So we begin by writing all of these original points. I'm going to try to be lazy, and I'm going to try and, oh, I don't know where it went. Oh no, I did something weird. Okay, more story, don't be lazy. Okay, so we're going to begin with negative 3 comma 0, negative 1 comma 3, 2 comma negative 3, and 4 comma negative 1. And in this example, what's going to happen is our function has a minus 3 over here. That means the entire function is moving down to 3 units. The x values are unaffected. The graph is not shifting side to side, so our x values will all stay the same, but every single y value is being subtracted by 3. So this is what we call our mapping coordinates, x comma y minus 3. The x values will stay the same, negative 3, negative 1, 2, and 4. And every y value over here is going to be subtracted by 3 to give you your brand new y values. So 0 subtract 3 is negative 3, 3 subtract 3 is 0, negative 3 subtract 3 is negative 6, negative 1 subtract 3 is negative 4. We're going to graph this, and when we do that, we're hoping every single point has moved down 3 units. And then we're going to label this y is equal to f of x minus 3. The value of c is negative 3, and the way we would describe this is it is a vertical translation 3 units down. Graphing those functions. Okay, so let's go on to the next question. It says, sketch the graph of f of x is equal to square root x minus 4. But I want to start off by actually graphing the parent function, which is the function we learned yesterday. So every single time I do a question like this, I'm always going to give you 2 grids. The one on the left refers to the parent function. We always start there. Do you guys remember what x values we used for our square root graph? Yep. Yeah, and if you have done your practice and you've done enough questions, this becomes so automatic that you don't even have to really think. You just know that those are the points you always use when you're doing a square root function. Someone in my other class said, do we have to use those? You don't. You could use any square root. The only thing is, if you were to use like the x to be 100 and the square root is 10, it doesn't fit on our graph. So if you want the numbers to fit nicely on the graph, use these ones. They will always work. Okay, we're also going to graph our parent function on this grid. And I'm going to call this f of x is equal to square root x. Now, on the right-hand side of the table of values, this is our new function that they're telling us to graph. So they're telling us that we're going to graph the square root function, except we're also going to subtract 4, which means we're going to move it down 4 units. We could just take all of the points on the graph and move them down, and we'll probably get the right shape. But again, inefficient, because when we get to harder questions, it won't make sense. So we're going to use our mapping coordinates. This graph is only moving down. So is our x value affected at all? No, it's not. And so we're going to keep all of our x values the same. So it's going to be x. Every single y value is being moved down 4. So what are we going to write over here? We're going to write y minus 4. We're taking every y value and we're subtracting 4 from it. Okay, so in our table of values, the x's will all stay the same, 0, 1, 4, 9, because that's what we had in our parent function. But now for every single y value, we are going to subtract 4. So 0 subtract 4 is negative 4. 1 subtract 4 is negative 3. 2 subtract 4 is negative 2. 3 subtract 4 is negative 1. And when we graph this, we should get a square root function graph, but shifted 4 units down. And we label it f of x is equal to root x minus 4. The value of c is negative 4, and describing this, we're just going to say it is a vertical translation 4 units down. So just like I said before, the left-hand side of the table of values refers to our parent function. This is what we learned how to graph yesterday. I'll review it with you for the absolute. What does the absolute value sign do, by the way? Yep. It becomes positive. So the numbers I always use are -2, -1, 0, 1, and 2. Again, you're free to use anything you want. Just make sure when you are graphing it, it fits in the 10 by 10 graph I give you. So in my opinion, it's just easiest to use these numbers. And we're going to graph it as well. Okay, so here's my general shape for absolute value. Make sure you guys have arrows on both ends. Make sure you label your function, original function. Now on the right-hand side, I have my new transformed function. So for this function, it's basically telling me that I want to, just trying to see what color I have, it's orange. I want to take my absolute value function, and then +2 means I want to shift it 2 units up. So my entire graph is moving 2 units up. Are my x values affected if the graph is moving up? No. So in the mapping coordinate, my x's are all going to stay the same, and every single y value is going to have 2 added to it. So now you'd look at your parent function and you just do the math. All your x values stay the same, -2, -1, 0, 1, and 2. And then 2 plus 2 is 4, 1 plus 2 is 3, 0 plus 2 is 2. This is a 3, and this is a 4. Question, Sarah? Yeah, if yes, there can. Yep, there can. And I can tell right away when I put my points, every single point has shifted 2, so I'm on the right track. And then arrows on both ends, and we're going to label this f of x is equal to absolute value x plus 2. And to complete the question, the value of c is 2, and it's a vertical translation. Two units up. I know you may not like the rational function graph, but I really like it. The rational function graph is tricky because it has asymptotes. And this is the only graph where I'm not going to ask you to draw the parent function. And the reason for that is when there are too many asymptotes and too many curves, it gets too messy. So for this graph, we are going to write the parent function table of values, but we're not going to graph it. We're only going to graph the transformed function. Okay, so as a reminder, what numbers do I use for this? I use -2, -1. I have this random -1/2, 0, 1/2, 1, and 2. And we did this last class. We kind of worked it out, but now if you want, you can get a scrap piece of paper, or if you've kind of done a lot of the practice questions, you probably are starting to memorize this a little bit. Not memorize, understand it so well that you can do it quickly. That's what I meant to say. I'm also squishing it in, so it's not just you. Which one can't you see? Yeah, it's -1/2. It's -1/2. It's just a dash to show it's undefined. And remember, this is our parent function right here. And we're not going to graph it. Now, what we have is f of x is equal to 1 over x. That's our rational function. And then we have a -3. And this -3 is basically telling us that the entire graph is going to be shifting down 3 units. So just like before, our x values are unaffected, and every single y value is going to be subtracted by 3. And the reason why this tends to be tricky is because now you're dealing with fractions, and there's no way to avoid them. There will be fractions. If you would like, you can always get a scrap piece of paper and figure it out there, or you can just try to do a little bit of mental math, which we are going to do here. So -1/2 minus 3 is -3.5. -1 minus 3 is -4. -2 minus 3 is -5. Can't do anything with anything undefined, so it stays undefined. 2 minus 3 is -1. 1 minus 3 is -2, and 1/2 minus 3 is -2.5. Now, what you're probably wondering is what's happening to the asymptotes. So just look up here for a second. Don't write this down. In a parent function of the rational function, you guys know how we have asymptotes on y is equal to 0 and x is equal to 0, right? This graph, is it moving side to side? It's not. So nothing is happening to the vertical asymptote. Sorry, nothing is happening. It's moving down to, yeah, nothing is happening to the vertical asymptote. However, because the entire graph is shifting down 3 units, your horizontal asymptote is going to move along with it. So the vertical asymptote is unaffected. However, your horizontal asymptote is going to move down 3 units. I'm going to show you a trick to figuring that out very quickly. And that is, whenever you have a number over here, this number tells you that you're going to have your horizontal asymptote at y is equal to whatever number is written there. Okay, so that's sort of like the shortcut, quick way to figure it out. You look at that number, and that tells you you have a horizontal asymptote at y is equal to -3. Okay, so let's try and draw this out now. We know our horizontal asymptote is not going to change, so you're going to draw a dashed line going down. And you're going to call that your vertical asymptote at x is equal to 0. And that makes sense because the graph is only moving up and down. So the only thing changing is the horizontal asymptote, not the vertical. Then you're going to draw a dashed line at y is equal to -3. And you're going to label this horizontal asymptote y is equal to -3. Yes. No, because it's going through the y-axis at -3. And then you're very carefully going to plot all your points. we have a half comma -1, 1 comma -2, 2 comma -2.5. And remember from last class, we draw a curve, and the definition of an asymptote is when a curve gets really, really, really close to it without crossing it or touching it. So I just tend to draw a parallel line almost to the curve. Razu? A half minus 3. And it's really nice when you draw your curve and you realize how close it was to the asymptotes, then you know you're on the right track. You're going to label this 1 over x minus 3. The value of c is -3, and it's a vertical translation 3 units down. And just know vertical translations affect your horizontal asymptotes. If you want, make a note of that. But whenever you have a number outside of the function, it affects your horizontal asymptote. Here. All right, for the second type of transformation, we're going to talk about horizontal transformations. And for horizontal transformations, if you guys remember for parabolas, it's always inside of your bracket or attached to your x. And do you guys remember when we would always do the opposite of whatever it said? So, for example, Rahiman, if the number inside was negative, we would actually move to the right. And if it was positive, we'd move to the left. So we're going to do the same thing now. We're kind of going to do the opposite thing. Yeah. You were talking. Okay, so we have the same squiggly line graph. We're going to do both the transformations to it. Let's identify our 4 main points and write them down. And I'm just going to write it down here as well, because I know I'm going to need it again. For the first graph, we're trying, and also, sorry, let's label this y is equal to f of x. Now we're ready to start. So for the first question, it's asking you for what is f of x plus 3? X plus 3 means this graph is actually going to be moving 3 units to the left. And that means our x values are going to be affected. So our mapping coordinates is going to change the x value. And whatever you have in the question, you're going to do the opposite for your mapping coordinates. So if the question said x plus 3, in your mapping coordinates, you're actually going to write x minus 3. And that's how you ensure that it's going to be actually going to the left. So just remember that little rule, and you should be fine for all the questions. Because there is no vertical transformation, the y values are unchanged. So now you're kind of doing the opposite. The y's will always stay the same, the x's will change. So -3 minus 3 is -6. -1 minus 3 is -4. 2 minus 3 is -1. 4 minus 3 is 1. When I graph these points, I should notice that my graph is going to be moving 3 units to the left. And I'm going to label this y is equal to f of x plus 3. When you're trying to figure out what the value of d is, you're actually going to look at the question and take the opposite number. So it's going to be -3. And to describe this, we're going to say it is a horizontal translation three units left. And that's it. We can see our graph has moved 3 units to the left. That means our table of values is correct. everything works. Any questions? Okay, horizontal is always a little bit tricky because you have to remember to always do the opposite. Let's do the next one. So my graph says y is equal to f of x minus 1. That means in my mapping coordinates, I'm going to write the opposite, which is going to be x plus 1. So every x value is going to have 1 added to it. And every y value will stay the same. And when we graph this, we should notice that our graph is moving 1 unit to the right according to the original function. And I'm going to label this y is equal to f bracket x minus 1. Our value for the letter D is going to be the opposite of whatever the original question was. So it'll be a 1. And this is a horizontal translation. One unit to the right. So the question was, why is the value of D always the opposite? And it's because the actual formula is x minus D. So in the first question, we have x plus 3. The only way to have gotten that is if you did x minus negative 3. And that's why the value for D is negative 3. That's like the actual definition. I always just think about it is it's just whatever the opposite is in the question. All right, we're going to do this 3 more times with all of our functions, and then we're done. We're going to do this a little faster. So for the parent function, go ahead and go ahead and draw them out for all of them, and then we'll just focus on the transformations. So maybe I'll do that first. I know it's repetitive, but the good thing about it being so repetitive is now, hopefully, at the end of this lesson, you guys are like, we're really, really good at graphing square root and absolute value. Parent function, when you have a square root sign and you have numbers inside of the square root sign, that's kind of what's considered the bracket in this case. So x minus 1 inside means there's going to be a horizontal translation, 1 unit to the right. Because negative 1, you're going to think of positive 1. It's always the opposite. Your y values are not affected, and your mapping coordinate is just going to be x plus 1, the opposite of what's in the question, and then the y will just remain a y. Okay, so 0 plus 1 is 1, 1 plus 1 is 2, 4 plus 1 is 5, 9 plus 1 is 10. This is a 0, a 1, a 2, and a 3. And when we do this visually, we should see our graph move 1 unit to the right. And it should have the same shape as the parent function. What is happening here? And I'm going to label this f of x is equal to square root x minus 1. The value of D is, if the question says negative 1, it's positive 1. and this is a horizontal translation, 1 unit to the right. Okay, absolute value graph. Let's go ahead and draw the parent function first. Okay, and for this, we have an x plus 4 all inside the absolute value sign, so that's considered to be inside the bracket. If it's plus 4, that means our graph is going to be moving 4 units to the left. That means every x value is actually going to be subtracting 4, and the y values will remain unchanged. So -6, -5, -4, -3, -2, -6, -5, 1, 4, 0, -3. And this graph is f of x is equal to absolute value x plus 4. The value for d is -4, and it is a horizontal translation 4 units to the left. More efficiently in their class. Okay, for the rational function, let's go ahead and write in our table of values. So we have -2, -1, -0.5, 0, 0.5, 1, and 2. This is -0.5, -1, -2, undefined, 2, 1, and 0.5. For the rational function, you guys, the quote unquote bracket is whatever number is attached to the x in the denominator. So in this case, see how the denominator has x plus 1? That means the entire graph is going to be moving 1 unit to the left. So our mapping coordinates are going to be x minus 1, and our y will remain unchanged. So we're going to have -3, -2, -1.5, -1, -0.5, 0, and 1. And the y values will stay the same. Now we got to think about the asymptotes logically. We know we have a horizontal and vertical asymptote. We also know the entire graph is shifting 1 unit to the left. So what's the only asymptote that's going to be shifting, Noel? Oh, yeah. Yep. So 0.5 minus 1 would just be -0.5. So when you're shifting your graph to the left, the only asymptote that's actually going to be changing is going to be the vertical asymptote. An easy way or a little trick to help you remember that is whenever you have anything in the denominator, that tells me that I'm going to have a vertical asymptote at x is equal to -1. Our vertical asymptote, or sorry, our horizontal asymptote is not changing, just our vertical asymptote. So we're going to have x is equal to -1. It's going to look like this. That is my vertical asymptote. X is equal to -1 because the entire graph is shifting 1 to the left. And then for my horizontal asymptote, that is going to stay the same. And it's going to be at y is equal to 0. We're going to graph really carefully, -3, -1/2, -2, -1, -1.5, -1/2, 2, 0, 1, 1, 1/2. And to finish off the question, the value of d is -1, and this is a horizontal translation 1 unit to the left. And for a horizontal transformation, the only thing that's going to change is the vertical asymptote. It's going to be shifted 1 unit to the left as well. Back to this, but if you're wondering, the only homework is handout B. So you guys at home, you can take a picture of it. It is from a textbook. It requires you to use your own graph paper and stuff, which is why if you want to do it, you can. Or you can go to your textbook and there should be just some general graphing there. If you guys have graph paper, then great. If not, then just print it off or I can try to get you guys some. I'm just gonna go back to this last question and you can go ahead and start working.